Yeah, hello. Welcome to lecture series on eicosanoids now. So in the last lecture, I talked about it was an introductory class to eicosanoids, how they are formed from arachidonic acid, right? So we talked about some examples of eicosanoids and where they are seen. Some are seen in the seminal fluid, in the menstruate, in the um, during labor, how they are being produced by the endometrium and all of that. Say that the first isolated by a scientist called von Euler in the prostate gland. So von Euler was the first person to discover the prostaglandins and all of that. And then ended the class by talking about prostaglandin E and F, which are actually the most important prostaglandins now. So that prostaglandin E1 and F1 alpha are both made from dihomogamma linoleic acid, right? Prostaglandins E1 and F1 alpha are both made from di that are both made from dihomogamma linoleic acid, dihomogamma linoleic acid. And diamogamma linoleic acid is the same thing as eicosanoic acid, right? So it's the same thing as trienoic acid. Specifically, the position of the double bond is 8, 11, and 14. So eicosa 8, 11, 14 trienoic acid. Also, we said that prostaglandins E2 and F2 alpha, which are also very much important. E2 and F2 alpha are synthesized from arachidonic acid, directly from arachidonic acid. And arachidonic acid, which is an eicosa 5, 8, 11, 14 tetraenoic acid, right? And then we said prostaglandin E3 and F3 alpha, E3 and F3 alpha are synthesized from eicosapentaenoic acid. So they're synthesized from eicosa 5, 8, 11, 14, and then 17 pentaenoic acid. So it was where we ended the class, the last meeting. So, but then I was emphatic in saying that arachidonic acid, which is the primary precursor to making these prostanoids, said arachidonic acid can be gotten from animal food, right, or from linoleic acid, which is a type of oil, plant oil. So linoleic acid can undergo, like we said, an elongation and desaturation reaction to give us arachidonic acid, and this arachidonic acid will then be incorporated into the membrane phospholipid. So the biosynthetic pathway is going to be kind of like this. We've got linoleic acid, which is an 18 carbon um, fatty acid with a double bond in carbon 9 and 12. So this linoleic acid is going to be desaturated. That means it's going to be oxidized by the desaturase enzyme, right? So specifically in carbon 6, so to give gamma linoleic acid, linoleic acid. So desaturation means that we remove two hydrogen, right? So we require NAD, NAD plus, right, to remove two hydrogen, and so we get NADH and H plus. So linoleic acid is desaturated in position 6 to give gamma linoleic acid. Gamma linoleic acid is an 18 carbon trianoic acid now. It's an 18 carbon trianoic acid with the position of the double bond. Now we have a new double bond formed in position 6. So it's now, we have three double bonds now. That's why it's a trianoic acid. And so the double bonds are seen in position 6, position 9, and position 12. So after the desaturation of gamma linoleic, after the desaturation of linoleic acid to give gamma linoleic acid, then there's going to be an elongation reaction. Two carbon is going to be added from malonyl-CoA. Malonyl-CoA is a 3 carbon compound with coenzyme A attached to it. So that definitely there will be loss of carbon dioxide, because when you add 3 plus 18 is supposed to be 21, but we're going to be getting 20 carbon. So one of the carbon is lost in form of carbon dioxide. So malonyl-CoA is attached, or reacted to with our gamma linoleic acid. Malonyl-CoA is a 3 carbon compound bearing acetyl-CoA, bearing coenzyme A, sorry. So it incorporates 2 carbon to the 18 carbon gamma linoleic acid. It incorporates 2 carbon to the 18 carbon gamma linoleic acid. So 2 plus 18 gives 20. So gives us a 20 carbon derivative called dihomo gamma linoleic acid, dihomogamma linoleic acid, which is a 20 carbon organic compound with 3 double bonds. Now, because of the addition of 2 extra carbon, then the position of the double bond changes along with elongation. So the new position of the double bond, when you're adding 2 now, you're adding 2 carbon. So the addition of 2 carbon, it affects the double bond. So you can just add 2 to the positions of the double bond. So from 6, we do 6 plus 2, that is 8. 9 plus 2, 9 plus 2 is 11, and 12 plus 2 is 14. So the new position of the double bonds will change. So this gives us dihomogamma linoleic acid, and the enzyme that first catalyzes this process is an elongase enzyme. Elongase. So let me just reiterate, starting with linoleic acid, which is an 18 carbon fatty acid with 2 double bonds in position 9 and position 12. We said that this enzyme undergoes desaturation in the presence. This fatty acid undergoes desaturation in the presence of the desaturase enzyme, which removes 2 hydrogen from carbons 6 and 7, right? Removes 2 hydrogen from carbon 6 and 7 in the presence of the cofactor NAD plus, coenzyme, sorry, presence of the coenzyme NAD plus. So, and then because of the introduction of a new double bond in position 6, we now have an 18 carbon organic compound with 3 double bonds. So the double bonds are on carbon 6, carbon 9, and carbon 12. So this new compound that is formed is called gamma linoleic acid. It's an 18 carbon octa octa 6912 trienoic acid. And 18 carbon octa 6912 trienoic acid. So afterwards, there's going to be incorporation of 2 carbon to the 18 carbon. 2 plus 18 gives 20. So there will be incorporation of 2 carbon to the 18 carbon to give 20 carbon, to give a 20 carbon compound, which is our dihomogamma linoleic acid. Now, the organic compound that is introducing these 2 carbon is malonyl CoA. Malonyl CoA. And malonyl CoA is a 3 carbon organic compound bearing coenzyme A with it. So, but out of the 3 carbon coming from malonyl CoA, it is attaching 2 carbon. It is binding 2 carbon to the 18 carbon from gamma linoleic acid to give a 20 carbon compound. So the remaining 1 carbon is going to be lost to carbon dioxide. So this reaction is increasing the length of gamma linoleic acid from is increasing the length of gamma linoleic acid from 18 carbon to 20 carbon. Hence, the reason why this reaction is catalyzed by the enzyme elongase. Now, because we are adding 2 carbon to our gamma linoleic acid, the addition of the 2 carbon will cause a change in the initial position of the unsaturation, the double bond. The double bonds that used to be in carbon 6, 9, and 12, the position changes. You just add 2 to the number. 6 plus 2, 8. 9 plus 2, 11. And 12 plus 2, 14. So if you had added 3 carbon, then the position would have changed from, let's say, 6 plus 3, 9, or 9 plus 3, 12, 12 plus 3, 15, like that. But we're adding 2 carbon in an elongation reaction, hence the reason why there's the change. So, and that's how the dihomogamma linoleic acid is formed. So after the formation of the dihomogamma linoleic acid, then dihomogamma linoleic acid is going to undergo desaturation in the between carbons 5 and 6 to give us arachidonic acid. Okay, in continuance, on continuation, the dihomogamma linoleic acid that was formed, which is an eicosanoid acid, we then undergo desaturation in carbon position 5 between, so the 2 hydrogens from carbon 5 and carbon 6 is going to be removed, right, in the presence of the enzyme desaturase, which is catalyzed by NAD plus, and it gives us our arachidonic acid. So arachidonic acid is a 20 carbon organic compound with 4 double bonds. The position of the double bonds are seen in carbons 5, 8, 11, and 14. Now, this arachidonic acid that is formed will then be esterified with membrane phospholipids, right? Being esterified with membrane phospholipids. So remember, the phospholipids that we can find in the cell membrane can either be phosphatidyl serine, or could be phosphatidyl choline, or could be phosphatidyl inositol, or could be phosphatidyl ethanolamine, right? So in a nucleophilic substitution reaction, um, the arachidonic acid becomes esterified with the membrane phospholipid, and the enzyme that catalyzes this reaction, if the membrane phospholipid is phosphatidyl inositol, for instance, the enzyme catalyzing this reaction will be acyl CoA. Like, the enzyme catalyzing the reaction is going to be acyl CoA lyso phosphatidylcholine, choline, acyltransferase, abbreviated as LPLAT, right? So the enzyme is acyl-CoA lysophosphatidylcholine acyltransferase. So it's a transferase enzyme. Sorry about that. It's a transferase enzyme that transfers the acyl group from transfers the arachidonic acid, binds it to phosphatidylcholine, right? So it's just like saying that, we've got our cell membrane, which is seen in the phospholipid bilayer, right? So these are phospholipids, right? Without, this is the head, the polar head, polar head, and the non-polar tail. So then we get these molecules of arachidonic acid coming to bind. These molecules of arachidonic acid coming to bind or incorporate themselves to these phospholipids. So they attach themselves to these phospholipids, and this is facilitated by a transferase enzyme which is called acyl-CoA lysophosphatidylcholine acyltransferase. Okay, so after the incorporation, we now have a cell membrane with arachidonic acid bounded to it. These are cell membranes. These are attachments, these are phospholipids from cell membranes with arachidonic acid bound to them, right? So we have arachidonic acids bound to them. So what happens next is that the process of synthesizing our eicosanoid, this arachidonic acid has to be released into the cell. So the arachidonic acid is cleaved off from the membrane phospholipid by the enzyme phospholipase A2. This is a very important enzyme, and this step is a rate determining step, right? It's a rate determining step in biosynthesis of eicosanoids. So the enzyme here is phospholipase A2. So phospholipase A2 will cleave off the attached arachidonic acid from the membrane phospholipid. So we will have free flowing arachidonic acid inside the cytoplasm of the cell. So the arachidonic acid that is then released can then undergo a cyclooxygenase pathway to give us um, prostaglandin, or can undergo the leukotriene pathway, to give us leukotriene like that. Yeah. So just to remind you, to reiterate again, we said we've got a membrane phospholipid now bearing our arachidonic acid, right? So we've got phospholipase A2, which is the enzyme here. We cleave out arachidonic acid. So to release free arachidonic acid, from the membrane phospholipid, and this cleavage is facilitated by the enzyme phospholipase A2 in a rate limiting step. So after the release of free arachidonic acid, the arachidonic acid can undergo two pathways. One is the cyclooxygenase pathway, which is catalyzed by the enzyme cyclooxygenase. So there are two isoforms of this enzyme. Can be cyclooxygenase A2, it can be cyclooxygenase 1 or 2. So the first pathway is cyclooxygenase pathway. The cyclooxygenase pathway give rise to the formation of prostaglandins. Can be A, B, C, D, E, F, or give rise to the formation of thromboxanes, or give rise to the formation of prostacyclins. So you can have prostaglandins, you can have thromboxanes, or you can have prostacyclins being formed from the cyclooxygenase pathway. While for the arachidonic acid can also undergo a different type of pathway if it is catalyzed by the 5-lipoxygenase enzyme, which is facilitated or assisted, if you will, by the 5-lipoxygenase activating protein FLAP protein, 5-lipoxygenase activating protein. So it undergoes this lipoxygenase pathway to give leukotrienes, or to give it gives us leukotrienes, or it gives us 5-hydroxy eicosanoid acid, that's HETE, 5-eicosatetraenoic acid, or it could give 5-hydroperoxy eicosatetraenoic acid. I'll take it again. So the membrane phospholipid will be cleaved so as to remove the incorporated arachidonic acid, and the enzyme that catalyzes this process is phospholipase A2. So after the cleavage of arachidonic acid from the membrane phospholipid in the presence of phospholipase A2, then the free arachidonic acid can then undergo two biosynthetic pathways catalyzed by two different enzymes. It can be the cyclooxygenase pathway, which is involved in the formation of prostaglandins or thromboxanes or prostacyclins. Or we could also have the lipoxygenase pathway, which helps to form leukotrienes or 5-hydroxy eicosanoic acid, or we could also have formation of 5-hydroperoxyl eicosatetraenoic acid. So in the next lecture, we'll be looking at the cyclooxygenase pathway. So till then, Philaretus. All right, thanks, and God bless you.